inflows and outflows of quasars. So go ahead.
Okay, thank you, everyone. Continuing on talking about studies of black holes and what the proposed mission axis can tell us about these black holes. My talk will be focused on X-ray lensing and of the inflows and outflows of quasars. So let me first start with introducing some of my collaborators, and I would like to mention Henrik, who's done a lot of the simulations that I'll show, and actually a lot of the monitoring in the optical and UV have been done by Christopher Morgan. So you've seen this picture, I'm assuming many times, but it's relevant to the talk, so I'm going to say a little bit about it. So we know that most of the X-rays in quasars originate from the hot corona, but a small fraction of them also originate from reflection. And some of the X-rays from the corona are reflected from near the event horizon, and some actually are reflected from further away. And the X-rays that are reflected nearby will be distorted due to general relativistic and special relativistic effects. So what does the spectrum of a disk look like? Well, let's start off with a very simulation that actually was done some time ago by Chris Reynolds. If you just illuminate a cold slab with an X-ray power law, you get this reflection spectrum that's shown here in the solid line, and you see a lot of these fluorescent lines with the dominant one being the iron line. Now, obviously, you don't see this reflection spectrum in a quasar, and the reason why is you have a disk that's rotating, and especially in either black hole, you have GR and SR effects. So these lines actually get relativistically blurred, but we do actually see the blurred iron line, but notice the other lines at lower energies are not actually resolved and not seen. There is a suggestion that some of the soft excess seen in AGN may be due to the blurring of these lower energy soft lines. So I'll get back to that later. So let me talk a little bit about lensing, and so I'll describe what macrolensing and microlensing is. So if you have a distant source between you and the observer, if there is a galaxy, that galaxy can actually bend the light from the source. So in the case where the total gravitational potential bends the light, you have the formation of multiple images. So macrolensing produces multiple images, and then in addition, magnifies. You get a magnification that can go from a few to 100. So microlensing, though, is the bending of light produced by individual stars in the galaxy. So microlensing does result in splitting of images by almost a tiny amount, like micro arc seconds. That's why it's called microlensing, but it's different for every image. Now, the important thing about microlensing is that the stars produce a set of magnification caustics that essentially go over the, move across the accretion disk and magnify slices of the accretion disk as these caustics go across. So you can imagine this caustic slowly going across the accretion disk and gets closer and closer to the event horizon, and will be magnifying the emission that's coming closer and closer in to the event horizon. All right. So another property of microlensing is that it affects compact objects more strongly than extended objects. So for example, we know that the X-rays are more compact than the optical disk. So we expect that the microlensing to affect X-rays more than the optical light in a quasar. So we actually have monitored about a dozen gravitational lens quasars with Chandra, but the one quasar that we have actually monitored the most is RX J1131 over 15 years. And on the left, I'm showing you the Chandra image of this quasar, and you see 4 images. And the bottom left is the stacked image. And on the right, what I'm showing you is the light curves, but I'm showing you the ratio, the flux ratio between 2 images. So for example, in the top panel, I'm dividing the light curve of image A divided by the light curve of image C. And then the middle one is B over C and D over C. The black data points are the optical data and the blue data points are the X-rays. Now, why am I dividing the two images? By dividing the light curves of two images, you essentially remove the intrinsic variability. So the only variability that is left is due to this microlensing variability as the caustic is going across. So you clearly see that these ratios are not flat. And you can actually see in the first panel, image A is showing significant, over the 15 years of monitoring, microlensing events. You can see in the middle panel, the image D is also showing at a different time a microlensing event. And then in the last one, also image D. So you can see we've detected these microlensing events going on. All right, so one of the very interesting results that we obtained by analyzing these light curves, and remember the effect that I mentioned that smaller regions are affected more strongly by microlensing, we're able to constrain the size of the X-ray emitting corona. And on the y-axis, I'm showing the half-light radius of the X-ray emitting corona, and on the x-axis, the mass of the black hole for several black holes for which we actually applied this technique. And you can actually see that the corona size is very compact. The dashed line is 6Rg. So essentially, it's the innermost stable circular orbit for a non-spinning black hole. So these coronae, hot coronae, are very compact. And this is actually being confirmed with independently with reverberation mapping. So this is a very nice result that was, I think, came out first in around 2010. And since then, we've actually added more objects. Now, having said that now, though, we have, in many AGN, we detect at lower energies, essentially below 1 keV in the rest frame, an excess of X-rays, which some scientists think that it's due to an extended corona. That in this particular model, in addition to the hot corona, it's posited that there's also an extended corona, a warm corona, that produces the soft excess. But there's also another group that suggests that the soft excess is due to the blurring of these reflected lines. So there are these two models that are competing about what's causing the soft excess. And here's where AXIS actually can test these two models. Remember I said that we constrained the X-ray corona size. We actually can do the same with the warm corona if we actually apply this microlensing light curve technique to photons with energies below 1 keV in the rest frame. We actually cannot do that currently with Chandra because in the rest frame, in 1 keV rest frame, Chandra's effective area in most of these quasars is very low, and we actually can't do this. But AXIS will have first a much larger effective area below 1 keV in the rest frame, and could actually do such a we can actually apply this technique and resolve this issue. So going back now to the actual spectra of microlensed quasars, what do the spectra look like? Well, on the left, I'm showing you a typical spectrum of an image that's microlensed. And the dashed line shows where the ion K alpha line should be at 6.4 in the rest frame. And we've detected shifted lines, which we interpret as being due to the GR effect. As the caustic gets very closer and closer into the event horizon, the lines get redshifted more and more. So we've seen in many cases when there's microlensing, we see only in the image that's microlensed, we see these shifted lines. So we've produced now, this is the most updated distribution of these shifts, all right, of these ion lines. So if there's no shift, obviously the line energy should be at 6.4, but you notice here in this plot, there are cases where the ion line is shifted all the way down to 2 keV. And you notice it's like a barrier there that there's nothing below that. And so what we think is happening over this 15 years, we've accumulated a lot of data with different shifts. And at the point where the caustic is the closest it can be, close to the ISCO, this is represented by this this boundary here at about 2 keV. So one can actually calculate based on the Kerr solution what these G values should be for a given radius and a given spin. So essentially this G value, that means the amount of shift due to GR and SR effects, can be calculated if you know, for example, the spin of the black hole, the inclination angle, the radius of the ring, and the azimuthal velocity of at that particular radius. So we did that. We calculated in the middle panel here, middle top panel, the G values, and notice is the G max and G min values as a function of the radius, the distance from the black hole. And the reason why there are two min and max values for a given ring is one case corresponds to emission coming towards you and the other one for emission going away. So we take the observed distribution of shifts that we observed, and we find what consistent value of the emitting region do we get. And we find that the emitting region, the one that corresponds to these shifts at about 2 keV, corresponds to an ISCO radius of about 3.3 Rg. All right. So we constrain the ISCO radius, assuming that that boundary is the innermost stable circular orbit. And then once you know what the ISCO radius is, you can then calculate what the spin parameter of this black hole is. So we actually, for the first time using microlensing, have constrained the spin of a black hole, and this one is at a redshift of 0.658. And this technique can be used more efficiently by axis and actually constrain the spins of a variety of black holes at the different redshifts. And as Fabio mentioned, at low redshifts, we can use a different technique to constrain the spins of safer galaxies, but it's much more difficult to apply that technique to higher redshifts, and this might be an alternative to determine the spin of higher redshift quasars. Now, a more exciting result, very recent result, is the following. Well, we detected the shifted lines, so we said, well, what about those soft lines? Are they present in those microlensed spectra? So we did a blind search for cases where we have detected an ion line to search for additional lines. And indeed, we did detect in many cases, in addition to the ion line, additional emission lines. But not only that, but the emission lines we found were consistent with magnesium, silicon, sulfur, and argon, and shifted by the same amount as the ion line. So this is one case. I can show you many more, but to give you an example of what Chandra, this is a Chandra observation, what axis can do. I'm showing you a simulation of a 50 kilosecond axis observation of how axis could actually very nicely resolve the lines, determine the centroid of the lines very accurately to about 5 eV, which is very important, as I'll show later on. So for the first time, we've actually resolved, let's call it part of the soft excess, and the reason why the lines are narrower, remember, microlensing only magnifies a very small portion of the disk. So these lines are not as blurred as if you just image the entire disk, and that's why the lines are narrower. There's still, you expect some velocity blurring, but you're dominated here by the CCD resolution. So here I'm showing some more cases. On the left, I'm showing going from top to bottom. As the ion line shifts to lower energies, you notice the softer lines also are shifting to lower energies, and all the same thing also in the right panel. So as the ion line shifts to lower energies, so do the softer lines as well. Now, to get a more quantitative estimate of, do these soft lines really shift by the same amount as the ion line, we calculated the fractional shift of all the soft lines and compared them with the fractional shift of the ion line. So that's what I'm showing here. We calculated for all those soft lines, silicon, sulfur, magnesium, the fractional shift on the y-axis, and compare it with the fractional shift of the ion line. If they do track each other, that should have a slope of 1, and that actually is the slope that we find. So indeed, these soft lines are shifted by the same amount as the iron line. So here I'm showing a simulation by my collaborator Henrik, showing on the left a simulation of an accretion disk with a caustic going across, and on the right you see the spectrum, and you can see the iron line, how it changes as the caustic goes across, but you actually see the similar tracking of the soft lines as well. So we have been able to simulate some of the features that we see on observations, not all of them, but we're getting there. All right, so now, all right, I've showed you the spectrum that we detected of these soft lines. What fundamental property of the disk can we infer from these lines, and how can AXIS help us determine these properties? Well, I've actually created a simulation using silver. It's a code developed by Garcia et al. And I'm showing for a particular ionization parameter of log C of 1.5, inclination angle of 60, what the reflected spectrum would be. And this is, again, no GR effects, no SR effects. This is just like very far away, for example, from the center. Now, we don't observe this, obviously, because we have CCD resolution both on Chandra and proposed on AXIS. So what I did is convolve this with a CCD response. So all the different transitions from magnesium produce this broad line here. Magnesium, you see, this is what you expect to see with a CCD resolution camera. Now, I went ahead then and determined the centroid of these lines. And remember, the centroids of these fluorescent lines depends on the ionization parameter, all right? So in the next plot, I show you how, if you know the relative energy of, let's say, the sulfur line to iron, you notice it depends actually on the ionization parameter. So from this type of analysis, then you can see that how by measuring accurately the spectrum of all the lines in the centroids, you can constrain the ionization parameter of the accretion disk as a function of radius. But you actually, to do this, you actually have to know the energy of the line very accurately to about 5 or so eV. And so you need the high effective area that AXIS will have. And obviously you need the spatial resolution to resolve the lensed images with AXIS actually can provide as well. So this is actually a fundamental property that we can extract from measuring these microlensed reflected spectra. Finally, I want to show you another very exciting result from, this is a very recent Chandra observation of this object. So these are two observations of RX J separated by a few weeks. And you can see the reason, and this is from the most faintest image, image D. So the reason why it's plotted in this way, we had to use cache statistics to fit this very weak spectrum. And you see an emission line and absorption feature. We interpret this as being the result of microlensing of not only the reflected emission, but also the outflow from the quasar. And so based on that interpretation, if we assume that both the absorption feature and the emission feature are shifted by the same amount, we can estimate what the outflow velocity of this wind is. And we determined for the first observation where the emission line is shifted to close to 2 kV. This is like very close to the event horizon, as I mentioned earlier. The wind velocity is about 0.6 C. Now this seems very high, but remember the azimuthal speed of the disk very close to the event horizon is around 0.6 C actually. And for the second case where the lines are not shifted as much, the outflow velocity is about 0.34. So it's with an AXIS observation, this is how that spectrum would look like. So there will be no doubt that there's an emission line and absorption line there, and we can actually fit these with more realistic models to determine more accurately what's going on with these outflows, all right? So I want to quickly summarize some of the important things we can learn and constrain with AXIS. So AXIS will allow us not only to constrain the sizes of the hot coronae, but also of the warm coronae of quasars. It would allow us to constrain the ionization parameter of quasars, of the disks of quasars, the function of radius, and also allow us to constrain the spin as a function of redshift. As Fabio mentioned, learning about the evolution of the spin can tell us about the history of the AGN as well. Two synergies quickly. The synergy of AXIS with the Rubin Observatory is very important. Right now, we only know about 300 lensed quasars. Rubin will discover 10,000. This will be an explosion. A new field will be created. 10,000 AGN. And the fact that Rubin will be monitoring these means that we actually can trigger on a microlensing event, and for the first time with AXIS, follow up and obtain a single crossing event with AXIS. All right, and quickly, just to show why we need AXIS, most of the lens quasars have, you need a half power diameter of about 1 arc second to resolve most of the lens quasars that we currently know, and especially the ones that will be detected with Rubin. You need a half power diameter of at least, for example, a half power diameter of 2 arc seconds will only get you 30%. The final synergy is with eROSITA. Out of those 10,000 new lenses, we need to be able to select the ones that are X-ray bright to meet our science goals. eROSITA is currently doing a survey of the entire sky. I've actually started communicating with members of the eROSITA team to see how many of the current 300 week have been detected. I can't tell you the result, but it's very encouraging. So I think eROSITA will be very important for this synergy of telling us which one of those 10,000 are X-ray bright. So I'm going to leave you here with my conclusions. Thank you for listening, and I'm happy to answer any of your questions. Thank you.
Great. That was really interesting, George. That's pretty amazing what you can learn about the accretion disk. So I'll ask a quick question. Actually, we have several in the chat, so maybe we can go to those first. So Richard Rothschild is asking, what is the statistical significance of the soft lines above the continuum?
Yes, very good question. So each individual line is only detected to about 90%, but as a whole, so what we did, we ran Monte Carlo simulations. So with including the lines and not including, so all the cases that we've considered, the significance of all the lines together is greater than 99%. But I agree that if you just pick one line by itself, it's not significant more than about 90%. But as a whole, all the lines are significant to more than 99% using MC simulations. Yes, and as I said, the line, what's very interesting is the lines are shifted by exactly the same amount as the ion line. So that's an additional hint that we're onto something.
Okay, great. So the other question is by Mike Oraculus asking, what type of observing campaign would you need with AXIS to make the proposed measurements for a certain quasar? Like how many observations would you need? What period of time? And would you need contemporaneous optical monitoring?
Yes, that's an excellent question. I mean, the answer could be very long, and we don't have enough time because there are multiple topics. For example, I mentioned slightly about the one with Rubin, that Rubin will be monitoring the sky 3 times a week. So Rubin can tell us when a quasar is going through a microlensing event. In that case, we can immediately point, and you only need it doesn't have to be very quick because microlensing events last for maybe 2 or 3 months. And you can actually then do a campaign, let's say over a year, and select 10 objects for which you do single caustic crossing events, which will be very important for actually constraining GR by itself. Now, regarding spin measurements, you would actually select, maybe using eROSITA, the brightest candidates, and select at different redshift bins a number of quasars that are the best candidates. And that I think would have to be with consultation with other theorists, like, what redshift spin should we pick? But I think, again, I could go on and on, but essentially, the exposure times you would require to do this with axes will be significantly shorter, at least by a factor of 10. And remember, I want to mention that below 1 kV, axes will be a factor of maybe 30 or 40 more efficient than Chandra right now, because of the degradation of the effective area of Chandra. So you can do these observations much faster with axes than you were capable of doing with Chandra.
Great. So are there any last minute questions? If not, maybe it's a few minutes after the hour. So yeah, let's end this. And I wanted to thank everybody for coming. Some really good talks. Really interesting to see what you can do with high resolution on these black holes and microlensing events. So we'll have our next talk in a month. And thank you everybody for joining. These were really great talks, really interesting.